Reaction Workup 1. Extracting, washing, and drying.
As all chemists quickly learn, it is very rare for a chemical reaction to provide only the one compound that you're looking for. Even highly selective reactions generate the desired product as a crude mixture containing byproducts and unreacted starting materials and reagents. Liquid-liquid extraction is the most common technique for separating a compound from a complex mixture. In an extraction, you can take advantage of differing solubilities to selectively separate the different components. By carefully planning out an extraction and washing sequence, otherwise known as a workup, the desired product can usually be separated from the unwanted impurities. This video will illustrate the proper technique involved in working up a reaction.
In an ideal world, each chemical reaction in the laboratory would provide only the desired product in its pure form. In reality, the product is almost always generated as part of a messy mixture of byproducts and side products. In short, garbage. Liquid-liquid extraction is a useful technique used to isolate the desired compound from a complex mixture. In an extraction, the mixture is partitioned between two immiscible solvents in a separatory funnel, otherwise known as a SEP funnel. The key is that the two solvents are mutually insoluble, so they form two distinct layers. One of the solvents is almost always water, and the other is an organic solvent of your choice. The different components of the mixture are selectively distributed in one solvent or the other, depending on their different solubilities. In this way, you can take advantage of differing solubilities to selectively transport solutes from one layer to another. In most cases, but not all, neutral organic molecules prefer the organic phase, while charged molecules and inorganic salts prefer the aqueous layer. By carefully planning out an extraction and washing sequence, otherwise known as a reaction workup, the desired compound can usually be separated from most of the unwanted impurities. This brings up an important point. What is the difference between an extraction and a wash? These terms describe similar but fundamentally different operations. An extraction involves pulling the desired compound out of a mixture of compounds, whereas in a wash, you are pulling unwanted impurities away from the desired product. In other words, you always keep the extracts and trash the washes. This might sound confusing, but it will hopefully become clear as we continue. The first step in an extraction and washing sequence, once you have decided on the appropriate solvents, of course, is filling the SEP funnel. It is a good idea to use an iron ring and a nice cushy cork ring to safely support the SEP funnel. Before you add any solvent, close the stopcock and place a clean, dry flask under the SEP funnel. This will prevent you from dumping precious material all over the dirty bench. The flask will save you if the funnel leaks or the stopcock somehow opened itself. When the stopcock is safely closed and the flask is in place, pour your two solvents into the SEP funnel. Use a SEP funnel large enough that you don't fill it more than 3/4 full. If it is too full, you won't be able to efficiently mix the solvents. This brings us to the next step, mixing and venting. It is important to mix the two solvents very well. This increases the contact surface area and allows the distribution of solutes to occur very rapidly. But use caution. Mixing will frequently cause pressure to build up inside of the SEP funnel. Pressure buildup is especially common when you are using particularly volatile solvents, like diethyl ether, or compounds that can generate gas, like sodium bicarbonate. Under acidic conditions, sodium bicarbonate will release gaseous carbon dioxide. Before any vigorous mixing, it is a good idea to gently swirl and invert the SEP funnel. Then invert the SEP funnel, holding the stopper tightly. Allow the liquid to drain away from the stopcock and point the tip of the SEP funnel away from yourself and other people. Slowly open the stopcock to allow venting. Now you're ready to really mix it up. Hold the SEP funnel firmly and shake it vigorously for several seconds. Once again, invert the funnel and vent it carefully. Repeat the shaking and venting until you no longer hear gas escape when you open the stopcock. Then set your funnel down and let the layers settle. Ideally, 2 layers with a nice clean interface should form very quickly. Unfortunately, things don't always go so smoothly. A thick, cloudy layer, called an emulsion, can sometimes form between the 2 solvent layers. An emulsion is a colloidal mixture of the 2 solvents and is frequently caused by the presence of fine particles in the solution. Getting rid of an emulsion can take some time, so if you know that you are likely to generate one, your best bet is to take pains to prevent it ahead of time. For example, gently swirling and inverting your SEP funnel will rarely cause an emulsion to form. You will have to spend more time mixing because swirling is not as efficient as shaking, but it may be worth it. Don't worry, if you unwittingly generated a monster emulsion, you still have a few options. First, you can just sit and wait. It might clear itself up, even if it takes a few hours. If you don't have all day to finish your extraction, try swirling the mixture gently and stirring the emulsion with a glass rod. If this doesn't work, add several milliliters of saturated sodium chloride solution to the funnel and swirl to mix. The sodium chloride increases the ionic strength of the aqueous layer and decreases the solubility of the organic solvent in the water. As a last resort, you may need to use vacuum filtration to filter your entire mixture through a pad of sea light. When you are carrying out an extraction and washing sequence, it is very important that you keep track of which layer is which and what compounds are dissolved in each layer. This means that you constantly need to be asking yourself, which layer is on the top? Which layer is on the bottom? One way to keep track of this is to know something about the densities of the solvents you are using. In every case, the solvent with the lowest density will be on top, and the solvent with the highest density will be on the bottom. This is helpful because you can generally assume that dilute aqueous solutions have a density around 1 gram per milliliter, similar to water. The organic solvent will be in the top layer if it has a density less than 1 gram per milliliter, such as hexane, diethyl ether, or ethyl acetate. The organic solvent will be the bottom layer if it has a density greater than 1 gram per milliliter, such as methylene chloride or chloroform.